According to the Global Burden of Disease study, in 2021, about 10 people died every minute due to problems related with high body mass index, or BMI. That's 5 million people in a whole year. Obesity and overweight are not just medical conditions, but among the most critical health challenges in the 21st century. It is classified as an epidemic that can impact the health and well-being of billions of people around the world. There is a very wide range of known causes for obesity and overweight, so complex that each case can show unique challenges and must be diagnosed properly by a physician. While there is a variety of treatments, it's not always an easy problem to overcome and can originate many undesired physical, mental, and emotional consequences for those who suffer from it, as well as their families and loved ones.
According to the World Health Organization, obesity is defined as an abnormal or excessive fat accumulation that may impair health. Similarly, overweight refers to having more body weight than is considered healthy for a given height, often due to excess body fat. These conditions are commonly measured using the body mass index, or BMI, which classifies individuals based on the ratio of their weight to height. Specifically, a BMI of 25 to 29 indicates overweight, while a BMI of 30 or more classifies obesity.
The prevalence of obesity has more than tripled since 1975, making it one of the fastest growing public health concerns. As of 2016, over 650 million adults were classified as obese, and an additional 1.3 billion for overweight. These numbers continue to climb, posing a significant risk to the global healthcare system. But why is this issue so pressing? The answer can be found in its associated health risks.
Obesity significantly increases the risk of chronic diseases, including type 2 diabetes, cardiovascular disease, and certain cancers. It also exacerbates conditions like hypertension, osteoarthritis, and sleep apnea, ultimately reducing life expectancy. These impacts are not limited to physical health. Studies have shown that obesity also correlates with mental health challenges, including depression and anxiety. Addressing obesity isn't just about losing weight. It's about improving overall quality of life, especially for high-risk individuals.
The term high risk in the context of obesity and overweight refers to the elevated likelihood of developing severe health complications and chronic diseases due to excessive body weight. Identifying high-risk individuals is critical for early intervention and personalized healthcare strategies, as highlighted by the studies focusing on different symptoms and illnesses associated with obesity and excessive weight.
Obesity and overweight can often be prevented if detected early. Timely interventions allows for the adoption of lifestyle changes, such as healthier eating habits, increased physical activity, and better stress management. Prevention strategies often focus on addressing modifiable risk factors like diet and sedentary behaviors while providing education about maintaining a balanced caloric intake. For individuals at high risk, personalized healthcare interventions, including regular monitoring, behavioral therapy, and sometimes pharmacological support, can reduce the likelihood of developing obesity-related complications.
Furthermore, early detection enables healthcare providers to address underlying factors such as genetic predisposition, hormonal imbalances, or psychological stress, which might otherwise lead to weight gain. Community-level actions, such as promoting access to healthy foods and creating environments that encourage physical activity, also play a vital role in prevention. This highlights the importance of routine screening and public health initiatives in mitigating the obesity epidemic.
What if we could predict and classify obesity using artificial intelligence to combat this epidemic? Healthcare practitioners and researchers are turning to innovative and modern tools like machine learning. By analyzing patient data, predictive models can classify obesity types and identify key factors contributing to weight gain. I'm John Navizada, and today I want to show you how this predictive model can be a reality.
Hello, everybody. In 2019, authors Palencho and Manotas collected obesity-related medical data of over 2,000 patients from 3 different countries. This data included different features from gender, weight, and height, to other factors like overweight, history and family, eating habits, physical activities, and others. I'm Alex Pitting, and today we will show you our approach in understanding this data and building our own AI classification model.
I'm Israel Romeo, and today, my colleagues and I will describe our algorithm, our findings, and talk about potential applications of our machine learning model that can predict obesity levels with over 97% accuracy.
The first task is to always explore the data. The information obtained by Palencho and Manotas in 2019 contains 2,111 records, from which about 23% was gathered directly for patients in Mexico, Colombia, and Peru, and the remaining data was synthetically generated using Weka tool and the SMOTE, synthetic minority oversampling technique, to balance the data sheet, particularly for underrepresented classes. This combination of real and synthetic data provides a comprehensive result for analyzing obesity factors. These are the variables being captured in the data types: gender, male or female, age, in years, height, in meters, and weight, in kilograms. Family history with overweight, yes or no. Frequent consumption of high caloric food, always, frequently, sometimes, or no. Number of meals per day with vegetables, numeric. Number of main meals per day, numeric. Frequently of eating between meals, always, frequently, sometimes, or no. Smoking, yes or no. Number of water cups per day, numeric. Whether or not the patient monitors the calories in the food daily, yes or no. Physical activity hours per day, numeric. Number of daily hours of electronic device use, numeric. Alcohol consumption frequency, always, frequently, sometimes, or no. And the usual mean of transportation, automobile, bike, motorbike, public transportation, or walking. Some of the names of the variables are acronyms for their original names in Spanish for short. The last column in the data is the classification of the patient, which contains 7 possible values: insufficient weight, normal weight, overweight level 1, overweight level 2, obesity type 1, obesity type 2, and obesity type 3. We'll refer to this column as the target column, since this is what we are trying to predict.
After understanding the feature variables in the target column, the next step is to understand the data completion, as any missing record can lead us to the wrong conclusion. Fortunately, after reviewing the data, there are not missing pieces of information. Next, we must standardize and encode the data for all non-numeric columns, such as binary features and any categorical columns, including the target itself. These standardization allow us to set the data in a compatible format for the powerful machine learning tools in Python libraries. After the standardization and encoding, we proceeded to the exploratory data analysis, in which we use statistical tools to visualize the distribution of each feature and the target. For instance, we observed that the gender feature and the target classifications have a balanced distribution within the data. While height shows a normal distribution, age and weight shows a distribution skewed to the left. The rest of the features shows other non-standard distributions. This information helps us better understand how they behave overall. The following part of the analysis helps us understand the relationship between features and the target. This is usually known as the correlation matrix. The numbers shown in each cell of the matrix represent the correlation of each feature, giving a value from -1 to 1. Positive value means that 2 features grow simultaneously, while the negative value represents that 1 feature decreases as the other grows. You'll notice a diagonal in which all values are 1, which occurs when both columns and row represent the same feature. What we identified from this correlation is that weight and height have a positive correlation of 0.46, and family history with overweight has a correlation of 0.5 with weight. These correlations between features tend to represent a problem called multicollinearity that affects numeric predictive models, known as regression, but have a very little effect on non-numeric predictive models, such as classification problems like this one. We then focus on identifying the highest correlation of the last row, which is our target column. It's interesting to observe that gender, age, and height have a correlation close to zero, meaning that there's practically no relationship between those variables and the obesity column. While other features such as weight, family history of overweight, and CAEC, which represent the frequency question if patients eat any food between meals, have the highest correlations of all the features with a value between 0.3 and 0.4.
Common sense would suggest that perhaps gender, family history, and maybe even smoke could be variables that would help us explain the obesity classification, but the correlation analysis results told us a different story. Our approach will be to try different classification models with the same data and identify candidate predictive models that perform with the best accuracy. Following best practices, we divided our 2,000 records in 3 data sets: training, validation, and testing. 60% of the total records will be assigned randomly to become our training set. 20% will be taken as our validation set, and the last 20 will be used as our testing set. The training set will be used for models to learn from this data and can internally establish an algorithm to predict the target classification. Once the model has learned, we then see how it performs with unseen data. So we feed our validation set into the trained model and compare its predictions to the real values. For this exercise, we use the following models: logistic regression, random forest classifier, decision tree classifier, gradient boosting classifier, ADA boost classifier, bagging classifier, SVC, and MLP classifier. At this point, we passed all variables into the models, and we compare the results on the training and validation sets. To evaluate their performance, we use 2 metrics: the accuracy score, which describes how well a model compares to the true classification, and the F1 score, which also penalizes false positives and false negative errors, especially helpful with sensitive medical results. Comparing the performances of all models, we identified gradient boosting, random forest, and bagging as the best performers with accuracies of 92%, 92%, and 91% respectively. So we will focus on fine-tuning these 3 before our final selection. The next question would be, do we need all the features for our model? If we select only a few, does our prediction actually improve? How do we select if the correlations between the variables don't follow our intuition? Since the total volume of our training set is relatively small, we decided to take an algorithmic approach, developing a program that would calculate all the combinations between all the 15 features, and then run each one of the models with them. Worth mentioning that there are 65,535 different combinations of 16 features, and due to the exhaustive computational resources of the selected models, our execution test took over 7 hours to complete, but it was worth the wait. We obtained the best performing combinations, and the results surprised us.
There were several combinations that gave an accuracy above 95%, but there were 3 best predictive feature combinations that called our attention. Combination 1, which included features height, weight, ABC, frequency of caloric food, CH2O, number of daily water cups, and TUE, time using technological devices, gave the model an overall accuracy of 97%. Combination 2, which had features gender, height, and weight, resulted in 96% accuracy. While it is slightly lower, it only uses 3 features from the dataset. There were a few other combinations that resulted in 86%, but with several more features. But there was one very interesting combination that resulted in 95% of accuracy with just two features, height and weight alone, which we will refer to as Combination 3. Combination 3 is not only the simplest in terms of number of features, but also because these are variables typically measured on a regular doctor visit. This means they are very easy to obtain. Gender is also easy to obtain, so Combination 2 is almost as convenient. Next, we try to evaluate the performance of the three models, once more using only these three feature combinations, but using the testing set this time. Let's see if the prediction levels are consistent with the newly unseen data for the models. This experiment confirmed that the top performing features kept the expected results when using the testing set. For combination 1, the one with 5 features, random forest had an accuracy of 95%. For gradient boosting, it returned 94%, and the bagging classifier resulted in 93%. Then for combination 2, gender, height, and weight, random forest returned a 95% accuracy, followed by bagging classifier also at 95%, and finally gradient boosting with 93%. Lastly, for combination 3, height and weight alone, random forest and bagging classifier tied again at 95%, while gradient boosting returned to 93% once more.
To confirm that our results were not just the product of chance due to the initial randomly selected partition of the data, we decided to test the performance once more with multiple random samples of the same data. A reasonable expectation is that for some of these samples, the bagging classifier works better than the other two. In others, it'll be the random forest, and another fraction will be dominated by the gradient boosting. So there will be some overlap between them if we run them multiple times, but our goal will be to see if any of the three models outperforms the other most of the times. That will be the model that best fits the classification problem. For this task, we wrote another automation in Python to take those random samples and train the model 30 times. We decided to perform the test only with combination number 3, with height, weight, as it is the most simple and easiest to implement practically. When performing the experiment, we see that the expected overlap between the models occur, although it seems clear that the random forest is the algorithm that outperforms the other two more consistently, showing over 97% of accuracy most of the time.
So far, we've discovered that we can reach a slightly higher accuracy with combination 1, followed closely by combinations 2 and 3. Which combination should our model use? Our conclusion is, it depends on the data availability. If all 5 variables of combination 1 are available to the medical facility or research study, our recommendation would be to use all 5. Similarly, if only gender, height, and weight are available, but not the caloric food frequency or technological device usage, the model can work with those 3 and still predict over 97% of cases accurately. Lastly, if only height and weight are available for some reason, the model can still predict 97% most of the time.
It is worth pointing out that while random forest is an algorithm that typically requires more computational resources than other models, for a daily use application with one patient at a time, the result would be instantaneous. However, in an environment that would be under more extensive research, running the random forest model would require a robust server environment for faster performance. Or at least timing should be considered before running a large number of classifications, since we did observe that about 1,500 predictions can take several hours on a regular personal laptop.
Still a lot of areas of opportunity. Improving the accuracy is obviously one of the first ones, as every false positive or false negative could lead into health consequences. Another area of opportunity is the performance of their algorithm. For future research, perhaps an upgraded version of our random forest algorithm can perform way faster. Lastly, we recommend getting new data sets from other countries and also explore new features to see if that information can provide a better and more enhanced precision of the model.
When it comes to applications, the sky is the limit. Think of a personalized weight management plan on a phone application that can help both the healthcare provider and the patient to work in a tailored dietary exercise regimens based on the individual's available information. Another possible application is right at the doctor's office to identify individuals at high risk and monitor the evolution of the situation on each visit.
Governments and NGOs could also use aggregated data to design targeted campaigns, programs, or allocate resources to communities with higher risks. This could be a great measure to proactively detect and fight obesity. Our classifier can also be used for clinical research, especially for specific obesity categories, or when analyzing the effectiveness of treatments or lifestyle interventions. It is worth noting that clinical research facilities typically come with sufficient hardware to process a large number of predictions with high efficiency.
Health insurance companies might use prediction to assess client risk profiles and design incentive programs for maintaining healthy weight levels. Fitness centers could also recommend tailored exercise routine based on predicted classification and physical condition for their clients.
These and many more applications can be based on predictive models like ours, saving lives with early detection. 10 people die in the world every hour due to a problem linked with high body mass index. I can imagine a world where that statistic goes down to zero and belongs only to the past. Let's take action and help detect overweight and obesity early.